Welcome to this session on multithreading in Unreal Engine. In this session, we will explore how to efficiently use multithreading to optimize CPU-intensive tasks in Unreal Engine. Let's dive in. Here are the learning outcomes for this session. By the end of this session, you will understand what multithreading is and when you should use it. You will be able to implement a CPU-intensive example and apply it in various multithreading approaches. You will also be able to compare different multithreading techniques like task graph, AsyncTask, ParallelFor, FRunnable, and task system to solve CPU-intensive problems. You will be able to identify common pitfalls of multithreading and learn how to address them effectively. With these outcomes, you will gain a basic understanding of how to implement and leverage multithreading in Unreal Engine to boost your project's performance. Multithreading is the ability of a CPU, or a single program in this case, to run multiple threads of execution at the same time. Each thread can handle a different set of tasks or computations. This is critical in modern software development because it allows you to fully utilize multi-core processors, improve performance, and keep your main thread, often the game thread, running smoothly for tasks like rendering and player input. In games and interactive applications, performance is key. Imagine you have heavy computations, AI pathfinding, physics simulation, complex data processing, or large amount of asset loading. If you do all of this on the main thread, you risk freezing the game or dropping frames where hitches, as many call it, appear. By offloading these tasks to background threads, you maintain responsiveness and deliver a smoother experience. But multithreading is not always the silver bullet. Some tasks are inherently sequential, and splitting them up might introduce complexity without performance gains. Also, multithreading introduces its own challenges: data races, synchronization overhead, and potential bugs that are hard to reproduce. We will talk more about these pitfalls and scenarios where multithreading doesn't help or isn't possible later on. Now on to the good stuff. In Unreal Engine, the game thread is the main thread that runs your gameplay logic, updates actors, processes input, and communicates with various engine subsystems each frame. Think of it as the heartbeat of your game's logic, the single thread that ensures all gameplay code runs in a safe and deterministic order. By design, many engine APIs and gameplay operations are not thread safe, so they must be executed on the game thread. Understanding the game thread's role is crucial, especially when introducing multithreading to your project, because you need to know what must remain on the game thread and what can safely be moved off of it. The game thread is the central execution thread, meaning it coordinates all gameplay logic each frame. It also runs actor ticks and updates, for functions like tick are called on the game thread each frame. Creating, destroying, or modifying these objects often must happen here in the game thread. It's also single and deterministic flow, since it avoids data races and ensures stable gameplay. It's not thread safe for many operations, since most engine calls must occur here in the game thread. Game thread is a key to multithreading strategy, for it determines which tasks to stay on the game thread and which can safely move off. To illustrate multithreading concepts, we will use a simple and familiar computational problem, which is finding all prime numbers within a range. Why prime numbers? Because it's a classic CPU-intensive task that can benefit from running in parallel. It's also easy to understand and measure performance. To illustrate multithreading concepts, we will use a simple and familiar computational problem, which is finding all prime numbers within a range. Why prime numbers? Because it's a classic CPU intensive task that can benefit from running in parallel. It's also easy to understand and measure performance. Here we have an enum called eTaskType that categorizes different multithreading techniques available in Unreal Engine. By defining these as blueprint accessible enum values, we can easily select and switch between various task execution methods from task graph on task system to FNonAbandableTask, FRunnable, AsyncTask, generic async, future and promise, and ParallelFor. This approach allows us to consistently reference each technique in our code, making it much simpler to experiment with and compare their performance. Here we see a snippet demonstrating how to use a sync function in Unreal Engine. With just a single call, we dispatch a lambda function to run on a background thread specified by Async execution thread pool. Inside the lambda, we loop through our chosen range of numbers, check each one using isPrime, and log every prime number we find. Thread pool here refers to Unreal's built-in thread pool. The engine automatically manages these worker threads, distributing tasks efficiently, so you don't have to create or manage threads yourself. This approach is simple and straightforward. By moving the computation off of the main game thread, we avoid stalls and maintain a smooth experience. However, if needed, you can also schedule the lambda to run on a chosen game thread by choosing a different async execution option. This can be handy for tasks that must interact with engine objects requiring main thread access. While we don't manage dependencies or return values here, Async offers a quick way to parallelize tasks or ensure certain code runs on the correct thread. As we move through, we will see more advanced techniques, but Async is a great starting point for anyone new to multithreading in Unreal Engine. Here we are using Unreal Engine's AsyncTask for multithreading, which allows us to schedule lightweight tasks onto Unreal's thread pool. This is a fire and forget approach, meaning once the task is dispatched, it will run asynchronously on the specified background thread without any need for manual management or waiting for results. Now we are looking at ParallelFor, a tool designed for data parallel tasks. Instead of manually creating loops and dispatching work across threads, ParallelFor does it for you. Here we just specify the number of iterations, in this case range, and provide a lambda that processes each index. For each iteration, we calculate the current number, which is start plus index, and use our function isPrime to check if it's prime or not. If it is, we log it out. Behind the scene, ParallelFor automatically splits the iterations across multiple threads, allowing the work to be done in parallel. This is especially efficient for large datasets or compute-heavy loops. You don't have to worry about thread management also or synchronization. ParallelFor takes care of disputing the workload and combining results efficiently. This makes ParallelFor a great choice for operations like batch processing, bulk computations, or any scenario where you have a large set of independent items to handle quickly and in parallel. Here we have an example of using FNonAbandableTask in Unreal Engine. This class represents a unit of work that the engine's task system will always complete once started. It won't be cancelled or abandoned mid-execution. In this example, we create an fPrime task, derived from FNonAbandableTask, which implements a doWork method. Inside doWork, we loop through the specified number range and check each number using isPrime. If it is prime, we log the result by wrapping the task in if auto-delete async task and calling start background task. We automatically queue the task on Unreal thread pool and ensure it gets cleaned up after execution. This approach gives you a more explicit representation of a standalone task compared to the simpler async calls. It's still relatively straightforward, but with FNonAbandableTask, you gain more control, like providing profiling stats with getStatID and ensuring the task can't be left half done. This is a great stepping stone before exploring more complex dependency-based systems like Task Graph or the new task system. Here is the core implementation of the future promise model. For the promise setup, we create a promise to hold the computed results. From this promise, we obtain a tFuture, which allows us to retrieve or chain results once the background computation finishes. For the background computation, we are using any background thread normal task using AsyncTask. We move the heavy prime calculation to a background thread. We then iterate over the range and compute prime numbers using isPrime. The prime numbers are stored in a local array called primes. But why mutable in the lambda? Mutable allows captured variables like promise to be modified inside the lambda body. In this case, we're calling promise setValue for primes. This marks the promise as completed and delivers the prime numbers as a result. Finally, the function returns the tFuture. The future can be used to trigger follow-up tasks, wait for results, or pass the calculated data back to the main thread. Now we can call calculate. We log that the calculation has begun. This helps track the execution flow. The doPrime calculation task is the function that starts the prime calculation. It uses a promise to compute results asynchronously and return them later. Once the heavy computation completes, we use .next to define what happens next. In this case, we move back to the game thread. Focus on this because we're going to use AsyncTask. For named threads, we're using gameThread to safely log the results back on the game thread. We iterate through the primes and print each one. This approach ensures that the heavy computation happens in the background, while the final results are delivered back to the game thread where it's safe to interact with engine objects and log data. Here we are using Unreal Engine's task graph system to calculate prime numbers efficiently on background threads. Task graph is a robust system for managing fine-grained tasks that can execute asynchronously and potentially in parallel. Using create and dispatch when ready creates a new task. Then, for each number, we call isPrime to check if it's a prime number or not. If the prime number is found, we log it. The last parameter specifies where the task will execute. Named threads, any thread tells the task graph system to schedule the task on any available worker thread, as we are used to. Task graph ensures efficient use of Unreal's worker threads by balancing and executing these tasks automatically. This is what we gain from task graph. It's lightweight, it's high performance, the tasks are very small and granular, and it's ideal for parallelizing operations. If needed, you can chain tasks together, ensuring tasks are executed in the correct order. Also, Unreal handles the allocation of worker threads, freeing you from manual thread management. Here we are introducing Unreal Engine's task system, which is a more modern and advanced multi-threading solution that improves upon task graph. It's designed for flexibility, better scheduling, and dependency handling, making it a powerful tool for multi-threaded operations. Let's break this example down. Launching a task with UE tasks launch is used to execute the lambda asynchronously. The first parameter, UE source location, is a macro that helps you debugging by identifying the file and line number where the task was launched. The second parameter is the lambda function that executes the task. Here we capture start and range by value to use them inside the lambda. For the calculation logic, we iterate through the numbers in the specified range. For each number, we call is prime to check if the number is prime or not. If the number is prime, we log it using UE log. These tasks run in the background, leaving the main thread free for critical operations like rendering and input handling. This example is very minimal way to use the task system. You simply launch a task and let it run in parallel without any complex setup. This is great for simple fire and forget tasks like prime number calculation. But there is also advanced features in task system. The task system supports advanced features like task dependencies, task pipes, and nested tasks. For example, with task pipes, you can build a sequence of tasks where each task automatically starts after its prerequisite task completes. These advanced features allow you to manage complex workflows and improve scalability for CPU-bound operations. Now let's dive into FRunnable, a low-level threading API in Unreal Engine that gives you a complete control over threads. This is ideal for long-running or custom tasks where you need more fine-grained control. We start by creating a class that inherits from FRunnable. In the constructor, we initialize start, range, and stop task counter for the calculation and thread management. Then we have the thread initialization. The calculate function creates an instance of FRunnable prime calculator that we created. A thread is explicitly creating using FRunnable thread create. Here we give the thread a custom name, FPrime_Runnable thread. This is the name I gave it to it. This allows the task to run independently on its own thread. Unlike other multi-threading approaches like task graph or task system, FRunnable requires you to manually manage the life cycle of your thread. Let's look at the execution flow of the thread. First, the init method. It is called once when the thread starts. Here, it simply returns true, indicating the thread is ready to run. Then we have the run method, where the prime number calculation happens. We loop through the range of numbers and check if they are prime using isPrime. A stop condition is implemented using ifThreadSafeCounter. If stop task counter is set, the loop breaks, gracefully stopping the thread. Then we have the stop method. The stop function is used to set the stop flag automatically using the stop task counter we used, and we increment it. This ensures the thread can exit cleanly when requested. Notice if run doesn't break, that means even if you close the editor, the code on the thread might still be running. It's worthy to try. It's a lot of fun. We have a lot of key points. FRunnable gives you complete control over the thread's behavior, including starting, running, and stopping it manually. This approach is ideal for long-running background processes where you need custom stop conditions and full lifecycle management. In summary, FRunnable is powerful but requires careful management. It's best used when other higher-level threading solutions don't provide the level of control you need. To test our methods, I have created a game instance subsystem. This subsystem has a function we can call from anywhere in the game, and it lets us decide which multithreading method to test. This function uses a switch statement to choose the threading method based on the enum we created eTask type. Each case calls the relevant calculate function for the selected method. This makes it easy to compare all approaches.
Now, let's dive into the practical side and see everything in action. First, open the Epic Games launcher, go to Unreal Engine tab, then go to the Library tab. Click the plus icon to add a new Unreal Engine version. If you already have versions installed, they will appear here. Since I have Unreal Engine 5.3, I will launch it. Next, I'll create a new project using the third-person template. Set it to C++ and click Create. In the Plugins tab, I'll create a new plugin. I'll choose the blank template and name it. Feel free to choose your own name, of course. Then I'll add the header and CPP files we created together in the slides. After building the solution, we can test how the code works. Now I'll create a new actor, give it any name for testing, and remove unnecessary events. Now I will add a box collision. Adjust its thickness to make it visible, and untick hidden in-game so it's visible while playing in the editor. Next, I'll add an onComponentBegin overlap event so when the box overlaps with the character, it will trigger the code. I'll cast the other actor to the character and then search for prime and drag out our subsystem that we have created. Then I'll call the calculate function and promote task type to a variable, making it exposed on spawn. This allows control over each instance of the actor in the level. To visually distinguish each box with an enum option, I'll add a text render. We need to set the text, but there is no default enum to the text option. I'll use enum to string, and Unreal Engine can automatically detect when we convert from string to text. Since we don't want the text to change during overlap, but rather show it ahead of time, I'll place the setup in the construction script. Now, I'll place the actor in the level for each multi-threading technique we have used. Now, let's test a range of 5,000, and as you can see, it runs smoothly without any hitches. Next, I'll compare this with running it on the game thread. I have already created a C++ function to check if a number is prime or not. So I will use it here and use a bool to print the numbers. I will loop over a range of 100,000. And now, as you can see, hitches start to appear. To confirm, let's run multithreading with the same range. And now, as you can see, this runs smoothly without issues. Notice that if we had a loading thropper in the UI, it would have caused hitches as well. I hope you found this tutorial helpful. This is a basic starting point for you to try and hopefully implement it in your own projects. Thank you for following along.